Okay, so we've been learning about mean value theorem, and this is a theorem where graphically we can explain it probably best, and it involves this. Like, let's say down below here, this is a graph of f of x, and we're only studying it from a to b, which means we're just picking 2 points on a graph. But we know that even though it's from a to b, that this graph technically is going to keep on going in some direction. It doesn't stop at A and B. We're just focused between A and B. And the theorem for mean value says that the secant line that is formed between A and B, this line, this dotted line here, is going to be equivalent to the tangent line. So if I found a point where the tangent line, we'll say right around here, is parallel. So some point on the graph, which we often call C, is the spot where the secant line and the tangent line have the identical slope. That if I found the slope of this tangent line, whatever the slope number is, it's equal to the slope of this secant line. So that's kind of what the mean value theorem is all about, that there's got to be this point C where that happens. And sometimes there's like 5 spots on a graph where this can happen, where there's tangent line and a secant line with identical slope. They're parallel to each other. Well, we're going to apply that today. We're going to come up with some application problems, and our first application problem is this one. For t values on the interval 0 to 4, the position of a particle is given by x of t equals t squared minus 2t. At what time is the particle's instantaneous velocity the same as its average velocity on 0 to 4? So when I read this problem, and you can pause it if you need to write it all down, but when I read it, I'm thinking mean value theorem right away in my head. Like, I know that it's asking me when is the instantaneous the same as the average. And so in my mind, I already kind of know what's going on here. I just need to figure out, well, what is the instantaneous and what is the average? So let's start with that first. Velocity instantaneously is the same as x prime of t. So what I'm going to do is I'm going to derive this function. I'm going to use the power rule, get the derivative, and this thing, t squared minus 2t, is going to equal 2t minus 2. And we're also at the same time going to figure out what's the average velocity. And the average velocity means no derivative necessary. That's when I'm going to do x of, let's see, 0 to 4 is my interval. So x of 4 minus x of 0 all over 4 minus 0. And we're going to plug 4 and 0 back into the original equation. So if we plug 4 into this thing, t squared minus 2t, we are going to have 4 squared minus 2 times 4. 4 squared minus 2 times 4. And then we'll plug in 0. Well, that's all going to be 0 over 4. And if we just clean this up just a little bit, we're going to have 16 minus 8, 8 over 4 equals 2. Alright, so here's what we've kind of discovered. We have our derivative, and we have our average rate of change is 2. So now what I'm going to do is I'm going to take this work, and basically I'm going to set the derivative equal to the average. When does the average rate of change, which I'm going to write here, average velocity, equal the instantaneous? So when does the derivative equal the average? So the average velocity was 2, and we want to know when is it equal to the instantaneous? 2t minus 2. Totally an application of mean value theorem. So we're going to solve for t here. We're going to add this 2 to the other side. Get 2 plus 2 is 4 equals 2t. And we're going to divide by 2, and we're going to get our answer here. Our answer is going to be 2 equals t. So to answer our final question, when is the average rate of change equal to the instantaneous rate of change? Well, now I can safely say at time equals 2 seconds, or time equals 2 minutes, or time equals 2 something. That is our answer. Alright, so let's look at another problem that's less obviously a mean value theorem problem. And, before we do that, I wanted to show you how this looks graphically. I almost forgot. Okay, so now we're not done with that last example. We're gonna graph it. We're gonna take that x of t equation that we originally started with, which was t squared minus 2t, and we're gonna put it on a graph here. So t squared minus 2t, well, t squared is indicating that it's a parabola. So it totally is a parabola. It actually kind of looks like this. It goes down, goes up, and out. This is x of t. It continues in the other direction. What we're really focused on, though, is if you go back and kind of read the interval, is we're focused on 0 to 4. That was our interval. So I'm going to write 0 to 4 over here on the corner of my graph. And at 0, we have a point at the origin. At 0, so I circled it, I put a point here at the origin. At 4, we actually have a point up on the graph up here, which is at, looks like 8 on my graph. So we're at 4 and 8 on the thing. So our secant line is a line that connects from 0 up to 4. That's my secant line. And the slope of that line is supposed to equal the tangent at our answer. What do we get for an answer back here? We got t equals 2. That means at 2, which is right here, our tangent line should, oh, that's not a very good tangent line, should be parallel. There's my tangent line, as best as I could draw it here. It's parallel to my secant line. And it sure looks like it, at least, on this graph. So that's kind of a visual of what we just found. At time equals 2, the tangent line and the secant line are parallel to each other. They have the same slope. Okay, so now let's move on to another example here that's less obvious. And here it is. This is a very traditional calculus problem. We have a trucker traveled a distance of 198 miles in 3 hours. If the speed limit was 55 miles per hour, does this trucker deserve a ticket? Okay, so I never like to give tickets as my question here. I don't like giving out tickets, but does this trucker deserve a ticket? That's our question. So logically, a lot of people already feel like they can figure out the answer to this question. They probably can. If you've ever heard of a speed trap, this is really common. The cops will set up a 2-station speed trap where they have a cop on one end of like a pass or something and another cop at another mile marker up ahead. And what they'll do is they'll track the cars that go by the first cop. And the first cop, it's literally like they're watching like, oh, a RAV4 Toyota just drove by me at 1 o'clock. And then the next cop at the next mile marker will write down, that same RAV4 just passed me and it's now 1:15. They'll look at the time and say, okay, how many miles do they travel in 15 minutes? And they'll figure out, do they deserve a ticket? That's a speed trap. And so people get kind of caught on this because what they'll do is they'll see the cops at the mile markers and they'll drive the speed limit, but after they turn the corner where the cop can't see them, they'll floor on the gas and they'll go really, really fast, breaking the speed limit. And then when they get around to the next mile marker where they see a cop again, they slow back down, they let their foot off the gas, and so they think, oh, I escaped the cops, they didn't see me speed. Well, if there's 2, 1 on each end, they've trapped you because they've done the math. They're using calculus. How cool is that? And they'll give you a ticket. So here's how the speed trap works. If at the mile markers, we figure out there's 198 miles in between the markers, and this trucker drives 3 hours in distance, we're just going to do 198 divided by 3 and figure out what's going on here. So 198 miles divided by 3 hours. This is the kind of math that the cops are going to do. And 198 divided by 3 is 66. So on average, this trucker went 66 miles per hour. That's definitely over the 55 mile marker. Now, the justification in our answer, so far, like, look, there's no calculus in front of us here. Here's how we're going to justify this problem with some calculus. Because on average, this is an average rate of change right here, the trucker went 65 miles per hour, or 66 miles per hour, we know that the average and the instantaneous must equal each other at some time, according to mean value theorem. So we're going to write a justification that explains this. So here is how I would write my justification on an AP test. I would say the trucker's average velocity was 66 miles per hour. According to the mean value theorem, there must be a time when the average velocity equals the instantaneous velocity. Now, this is super important. If you don't mention the mean value theorem, you probably wouldn't get the points for doing your justification if this was a problem on the AP test. And the reason for that is, I mean, they know you can do this math on the back page here. They know you can do 198 divided by 3 and logically figure out this answer of 66 miles per hour. They're not concerned about that math. What they're concerned about is, do you recognize mean value theorem when it's in the middle of this problem? That the average rate of change must equal the instantaneous rate of change. Do you see that? And so I'm going to explain that in my justification. I'm actually going to write a third sentence here. I'm going to write at the bottom. So at some time, the trucker's speedometer said 66 miles per hour. You should give him a ticket. Give him a ticket. Answer the question here. So the trucker's average velocity was 66 miles per hour, which means the speedometer must have said 66 miles per hour at some time. Give him a ticket. So applications of mean value theorem. And you can see, we took a fairly simple problem here and made it pretty complex, but it's kind of the idea that counts right now with mean value theorem, is just making sure you understand it.